Hi, good afternoon, and thank you to Michael, Andrew and Chantal for the invitation. I'm going to talk to you today about, not about the work at the AA we've been doing and are planning to do, but about work we've been doing over the last couple of years at a practice I lead called NEX, and how, in a sense, I've been very interested in trying to develop a way of thinking about architecture as research, and how to do that in a context of contemporary practice rather than academic research. So when thinking about the title for this conference, the agenda for this conference, it really struck me that in many ways prototyping in architecture isn't new. And the early years of the modern movement in particular can be read through a series of prototypes and mock-ups. Other people have even observed that architecture in itself is inherently prototypical, in that every building is in some way a unique response to site, local context, materials and budgets. So in a sense, one could think of architecture itself as always prototypical. I think also, if you look to other industries such as car manufacturing, boat building, aerospace, the prototype has occupied a central position in the design process in all of those industries. Over the last few decades in particular, they've all undergone massive changes in terms of their process, their design process and their engineering processes. That has taken advantage of CAD/CAM technologies, and that's resulted in dramatic improvements in quality, in performance, and a reduction in cost. Architecture, that hasn't happened in architecture, and there's been quite a bit of a discussion about why that is. But I think, for me, there's two striking differences between the architectural context and any of these industries. The first is that most of them benefit from economies of scale. That is, the significant investment in prototyping is offset through volume production of a finalized unit. And I think Michael mentioned Range Rover earlier, and the kind of spending they are prepared to invest in new models. But secondly, what's quite important is they benefit from closed manufacturing and supply chains, where they can very precisely control both the quality, precision, material performance of everything that goes into their systems. Architecture, in a way, benefits or doesn't benefit from either of those two fundamental features. So then we're left with a question, really, well, what is the prototype, or what is it to think prototypically with an architecture? And for us, I think we see two models. We've kind of become aware of two models in our own office that we try and develop. The first I want to call the design prototype, and in a sense it's an abstract model that has a specific proto-architectural quality that can be instrumentalized or used in differing ways across a number of projects. For us, we call these models prototypical, these design models. And this example here, we've all been living with for almost exactly 100 years, is, for me, the quintessential kind of prototypical design, or design prototype. It's, of course, you all know it's Corbusier's domino system. But for us, these kind of models reflect a kind of interest we have, a design, spatial, organizational interest we have, but remain abstract enough to be used in a number of different ways. Most importantly, I think for us, they give us a way to structure an architectural agenda in the office that can guide us beyond an understanding of design as a contingent solution to a specific one-off problem. So that is a way of structuring an interest across a number of projects that really gets us over just solving immediate design problems, or seeing design as a problem-solving exercise. Our second use of the prototype occurs during the design process itself, and I've tended to call this the kind of working prototype. And for us, it can be either digital or physical. The physical prototype, which I think Heinz Isler has a history of producing remarkable examples here, is that they don't necessarily have to be full-scale models, but they have to have a specific attribute that can be directly calibrated or correlated to a full-scale one-to-one installation. And in this case, he was using pneumatic models as literally a form-finding process. Of course, the other more recently familiar type of working prototype is the digital one, and that really is just a relational model where the relations or performance of the model is in some way calibrated to, again, the performance of a full-scale model. And Gary Technologies have pioneered the use of that in architecture, but again as a direct technology transfer from other industries. So I want to talk about 3 projects and how we've maybe developed this idea of the design prototype and the working prototypes. One of the areas of research that we're very interested in the office is developing knowledge and skills in terms of modern methods of construction. And that specifically relates to digital design and manufacturing and architecture. And I think underlying that is just an ambition to create the exceptional or extraordinary spaces, assemblies and components, but with very ordinary means. So really the challenge for us is how do you create very bespoke designs or systems that match or exceed standardized options in terms of their quality, their cost and their performance. A second thing that these 3 projects have in common is actually an interest. We've been quite interested in the use of wood, mainly because of its technical versatility, but also, I guess, a good environmental profile. And I think maybe we felt just an unexplored potential in terms of its aesthetics. So the first project I want to look at is called the Paris Court Centre in Dublin. It's an 18th century listed building in the city centre, takes up an entire city block, and basically is a kind of 4-story townhouse surrounded by an annex and a courtyard at the centre. It's Grade 1 listed, and our role in it was really to analyse the building and develop proposals, contemporary proposals for it, that in one sense restored the building or the qualities of the building to what they were, but also improved its operational and environmental performance. I'm not going to go into detail, but the reason I bring this project up is because, in a way, it begins an example of how we use these 2 ideas of the prototype. And the one we were interested in here was one we've been quite interested in, an inquiry into the surface or the nature of the architectural surface, and actually exploring that as a way of perhaps making it deeper, a bit more complicated, and almost like particleized as a kind of way of breaking it up and thinking of the surface as an assembly of a large number of components. So with this idea, basically this idea about the deep surface gets deployed across a courtyard roof initially. And the tectonic of the roof really arose from a desire to create a kind of very non-institutional quality of light in this space, something that was very variegated and echoed the kind of rhythm of the fenestration in the facades. So in some places there's a kind of very fine, even, diffuse background lighting of shade and shadow, where in others it's punctuated with clear kind of glazed openings to bring in this quite strongly contrasting light. And we spent a long time looking at how to control that light, how to develop a system of these components, both through varying the depth and the angle of elements, which you see on the left here, and then on the right about how that resulting aperture projected onto the wall surface. We looked extensively and built models looking at the sunlight penetration into this courtyard, because it effectively had east, south and west light, so it really got a huge amount of solar gain during the year. So the challenge was developing models that could limit the solar gain while also creating a kind of really quite dramatic introduction of sunlight into the system. And this model here, we began just looking at a number of apertures. Really what it was doing is finding the best place on this overall surface of the courtyard of where to put windows so that we would get sunlight on the walls rather than on the floor. And this kind of working prototypical model was something that actually just really was almost like a form finding or a position finding process in the case of this study. Structurally, we had a very interesting challenge as well. We had to span 28 meters and we didn't really have any room to offload beams of any kind of size like that. I think the maximum size we could fit was a standard truck because it was the city centre and there was nowhere to really assemble anything. So we came up with this idea of a kind of reciprocating structure that would be made up of smaller elements and stitched together in a kind of cruciform pattern to aggregate to a much larger system. As we tested this through a lot of structural models, it became apparent that actually it's just not going to work, certainly not in timber. I mean, the beams became so large to deal with the loads that the visual effect of the structural requirements became too heavy and also overloaded the perimeter walls of the building. So we ended up actually translating that into a steel structure with very similar principles to actually just reduce the load. It's a solid McAlloy steel structure. Around the same time, we actually entered a competition for a table, strangely enough. And it was a competition run by the Technology Strategy Board and a digital manufacturing facility here in London called Metropolitan Works. And the award was that they would assist the winners with developing a piece to pre-production stage and prototyping it. And for me, I was very interested in this idea of the table as a kind of social space, as a very intimate social space, and really questioning again this idea of the status of the surface. In some sense, we think about what we say is making up a significant, or most of what we communicate, but evidently it's only responsible for a very small part of it, and gesture and posture and all kinds of other things actually communicate far more directly what we mean and what we intend. And I was interested in this idea about maybe this surface is a little less emphatic in the way it separates above and below, and maybe it becomes something that has a slightly more nuanced quality that would engage in this kind of social game, let's say. So we basically took this design prototype of the roof and literally shrank it to the size of a table and said, what can we do? How does this kind of develop or become installed at another scale in another context? So in this case, the form of the lattice really was defined by not environmental conditions but social. So instead of sunlight studies and penetration, we were really looking at the actual penetration of the gaze and actually the way people sitting around this would see through certain parts of the table opposite but not immediately in the vicinity of them. And the whole model of this lattice was set up really according to those rules. So what you get is a very intricate field of about 500 or 600 pieces of timber that really vary to and fro in relation to the way people view and see this table. And that kind of complexity, that sort of, let's say, subtlety in this lattice really demanded an awful lot of prototyping. The whole logic, the tectonic logic of the system in this case was at such a small scale that it was quite easy to deal with. It was a very simple mortise and tenon joint, which is a kind of century-old technique. What arose through this, because of the variety within the system, was actually I think each one only had 2 instances of being the same. So on the one hand, you're dealing with a very traditional, let's say, craft technique, but on the other, there's an immense amount of complexity in dealing with all of these different angles and developing a system that could accommodate and cope with that. Materially, we selected walnut basically because it's strong and it can take a very fine level of detail, which as a furniture piece it required. And we ended up actually having, it was that fine in in the center in these fins that it was about 6 millimeters, which even in walnut still warped as it was cut by the machine because it alters the tension in the fibers. So we ended up building these central things out of a kind of 3-layered laminate of walnut to give it stability. And these were basically assembled in much the same kind of logic, this growing reciprocal structure, which you can see on the right there. And that reciprocal structure, we introduced this other idea of a kind of a recursion. The same game of the reciprocal structure happens at a larger scale. So it happens at the scale of the individual small piece and a slightly larger scale, which you can see being machined here. And that you can see on the underside there, basically. And what that did is it helped control the dimensional kind of creep over the whole piece and also helped with the assembly. I think the assembly took about 3.5 days with a skilled craftsman. And what I think we were interested in as well is that the final piece not only has this quality of the surface and the variability of the way it's perceived, but also a very close interaction with the space it's in. By putting a very simple light overhead, you get these extraordinary kind of patterns and atmosphere within the space. And that just shows you detail of the individual joints as they kind of just slot together. So finally, to take this idea of this design prototype into another context entirely, which was an experimental project we did for the Times newspaper and the Royal Botanic Gardens at Kew a couple of years ago. And the brief for this project was really a garden and pavilion that explored the significance of plants. All of the plants in the garden were selected for their medicinal, their commercial, their industrial uses, etc. So really the pavilion somehow had to be a reflection of that. But for us it also offered a very interesting opportunity to explore somehow a kind of a question about the relationship between the natural and the artificial. I think it also offered an interesting opportunity in the context of Kew of exploring the idea of a pavilion, the typology of a pavilion, and actually Kew is kind of full of these things. And what's very striking about all of them virtually is that is the importance of their silhouette, first of all, as this kind of object sitting in an 18th century landscape, and secondly, that they're actually a kind of destination and a device for framing the landscape once you're inside them. So in a way, the structure we designed, we intended it to be a counterpoint to that in two ways. Firstly, we wanted it to be really enmeshed with it through its sighting and its kind of texture of its surface, to be enmeshed in its surroundings. And secondly, it wasn't really a destination. There was actually a route through it, so it was meant really as a much more dynamic space, a space that, let's say, filtered its surroundings rather than framed it. And we began with this idea of, again, this deep surface. And we took what we had first come across, this idea of recursion or iteration in the table project, and we developed it in this a bit further. And what I mean by recursion is basically a simple rule or a constraint that is repeated again over and over, but each time potentially producing a different outcome. So, and in our case, it was repeated again at a different scale. So in the first scale here, we used two types of recursion processes. The first was an L systems process, which is basically just a mathematical way of describing a process of branching. So the growth of the tree, for example, or the way any natural biological or plant would branch. And there's a mathematical way of describing that. So we looked at that in a number of cases and varied stuff like the length of the branch, the angle they divided at, etc., etc. And what we found actually was it gave us a kind of primary structuring, let's say, of this space, of this garden, but it couldn't infill between the branches. And for us, it sort of gave this one-to-one correlation between the project and the scale of the project and the scale of what was around it. So what I mean by that is the scale of the branching was almost the scale of the trees around the building, and that's something we really wanted to avoid. So we kind of left that and began looking at something much smaller, and in a sense I thought it was important that the pavilion itself could maybe communicate the sensation of biology at a very unfamiliar scale for an experience. So we looked at some work on mathematical modelling of leaf venation, and for us that was a much more productive way of thinking about it. And in the end we selected a kind of mathematical process, a Voronoi process, which doesn't strictly model biology, but actually has kind of many of the qualities that you see in biological systems. And we started this process of doing this repeated, let's say, action at a number of scales by just the first iteration gave us a set of points that gave us about 21 cells, 21 large cells, and that became the primary structure of 140 millimeter timber beams. The second one within that then gave us a whole set of smaller cassettes, if you like, that were made out of 20 millimeter boards. And I think there was about 126 of those. And then an additional, once we had that, we basically wrapped this pattern over the kind of boundary that we were actually given for the pavilion. It was something that was already kind of predefined. And one thing we added to it at that point was really thinking about how this pattern would become spatial, would become deep, and would become this deep surface. And rather than just extruding everything backwards, we projected everything to a center point, which for us really centered the experience of being inside this pavilion in a much more dynamic kind of way, that everything went back to a single vanishing point. So standing in the center of it, it seemed that everything radiated out from you. And that, while that really increased the kind of sensation of being inside the pavilion as a kind of dramatic moment, it obviously created quite a lot of additional complexity in the manufacturing. Within those 126 cells, we then did a third kind of process of division, and that I think produced about 587 final cells, and they were produced in a recycled polypropylene, which was a sort of flat sheet technology material that we could just fold up into a 3D form. And that's basically the whole system there. That's a piece of it, how it goes together. You have the primary structure, which are the large beams, the kind of plate cells or cassettes which were 20 millimeter board, and then these fine infill cells. And the really amazing thing about this whole idea of repeating this recursion process was that, just like a plant, every single cell was unique. So through obeying a few simple rules, every single outcome was different. Every cell was different, every piece of timber was different. And that obviously, to be viable, both in terms of just managing the number of pieces and from a cost point of view, meant an entirely kind of digital workflow and a file-to-factory process. So the model actually was the entire construction document. And that was sent first to the timber manufacturer, and then we were the ones coordinating with the plastic manufacturers and the assembly people. And to get to that point, there was a process of very intensive kind of prototyping, both digitally and physically. Here you can see, just studying how these elements work, that we can achieve the kind of level of detail and precision we want. And the infill cells were really done quite simply using a kind of basic sign cutting technology, and just a set of instructions about how to connect them together before they were put into each timber cassette. So that's basically what we produced for each one. Each one is a kind of flattened out shape that gets cut, and then this gets assembled and clipped together. And that's the finished project in queue there. So you can see the inside there, that basically the kind of corners disappear, everything is at sort of 45 degrees and radiates out from the center. So I'd like to close by just saying, I mean, I think these projects, in a way, have shown you the two ways we work. Our work with the idea of the prototype, with the idea of the prototypical as a design prototype, and prototyping is a central part of our process. I think that the change and the developments in computer-aided manufacturing and cheap digital fabrication processes are actually really fundamentally changing the way we work, where we can bring an idea of prototyping that has traditionally existed for a long time in other industries into architecture in a very cost-effective way, where we don't need closed supply chains or massive investments in upfront kind of testing. And I think that's actually quite a fundamental change. And for us, it starts to kind of shift us from a model of design, test, and redesign to something that's much more about being able to test conditions very early on and actually develop a design that's, let's say, much likely to be much more closely fitted to possible constraints. And that's a very different model to I think, any of the models that have existed in earlier prototyping within architecture. Thank you very much.